So there is a simple pendulum, and you know this about the basic physics. Just a minute. Huh? Okay, so this is the simple pendulum. So the theta is the angular displacement. Okay, so I will take that as a variable x1, angular displacement, and its derivative is going to be angular velocity. Okay, that is theta prime. So this is governed by a mathematical model which is given like this, that is x1 prime is equals to x2 and x2 prime is equals to minus sin x1 minus bx2. So if you see this system, the critical points are, okay, so the critical points are when the right hand side is 0, that is one is the x2 is 0 and x1 is 0, that is right. So the 0 0 is one critical point, and the other critical point is x2 is always 0, x1 is can be n into pi. So you don't have n into pi on the plane, so you have plus minus pi, plus minus pi. These are the critical points. First, let us look at the critical point 0 0. Okay, so the stability analysis of 0 0. Okay. So we use the asymptotic linear system. So first let us look at linearized problem. So what is the linearized problem? So what is the linearized problem? So we have the x1 prime equals to say f1, x2 prime equals to f2. So we basically form the matrix where dou f1 by dou x1 and dou f1 by dou x2, right? So dou like this, dou f2 by dou x1 at the critical point. And the system becomes x prime equals to this matrix. Okay, so call it as df at 0 into x plus the terms of order of x squared. Okay, so if you see that f1 is x2 itself, therefore dou f1 by dou x1 is 0 and dou f by dou x2 is 1, and f2 is minus sin x1 minus bx2. So you can write the derivative of that, right? So therefore it's easy, right? So you can write the derivative, therefore you can write the linearized system like this. The linearized system becomes x prime equals to 0 1 1 comma minus b, plus there is the terms which are of higher order, right? So this is Rx is of higher order. So Rx is like order of x square as x goes to 0. Order of mod x square, right? So then we have to look at the eigenvalues. So eigenvalues of this matrix, say 2 by 2 matrix. So you can write the minus lambda 1 1 minus b minus lambda. So this is equals to lambda into b plus lambda minus 1. Okay. No, this is minus 1. because you write the derivative of this minus sin x1, that is going to be minus cos x1 at x1 equals to 0, it is going to be minus 1. So this is minus 1, so this plus 1. So this equation becomes lambda square plus b lambda plus 1. So therefore lambda is going to be minus b plus minus b square minus 4 by 2. So if you see this, this is minus so if you, so this has the some special cases. So what will happen to these eigenvalues? Okay, so the first case is, say when b square is greater than 4. So when b square is greater than 4, even then the b square minus 4, square root of b square minus 4 is less than b, right? B square minus 4 is less than b. Square root of b square minus 4 is less than b. So implies the negative real eigenvalues. Negative real eigenvalues. So this implies that by the theorem, that Lyapunov's theorem on linear asymptotic equations, linear equations, this implies that 0 is asymptotically stable. So the second case is when b square is 4 and b is positive. Okay. So when b square is 4 and b is positive, then lambda is nothing but minus b by 2. So again you have the negative repeated eigenvalue. So even in this case you have the asymptotic stability. So the system is going to be asymptotically stable. Now the last case is when b square is less than 4. Okay. So when b square is less than 4, this is going to be a complex eigenvalue, but still it has the negative real parts. Okay. Still it has negative real parts. The third case is when b square is less than 4. So this is complex but with negative real parts. Okay, so these are the case what we said as spiral points, spiral point. Okay, but since it has eigenvalues with negative real parts, by theorem that you have, that this is also going to be asymptotically stable. So the point 0, 0 is going to be asymptotically stable. Okay. 0, 0 is going to be asymptotically stable in all the cases. Now come to the, that means in the simple pendulum case, when x1 is 0 and x2 is 0, means that pendulum is at rest. Okay, x1 equals to 0 means angular displacement is 0 and angular velocity is 0. That means it is just at rest. Therefore, it is going to be stable. It's not going to move. The other point plus minus pi is that when it goes to pi, this is the angle. This is the angle pi. Okay, so we know that if you take a pendulum and then keep it on the top, it's not going to stay there. It is just comes down to 0. So the solution of this is not going to remain at pi 0. It is going to come to 0. So that means it is physically, you see that it is an unstable point. It is an unstable angle. So let us look at that. That is pi 0. So the second point is pi 0 or minus pi 0. Both represent on the plane the same things. At pi 0, okay. So this is that angular velocity. That means that you have pendulum is at rest. Okay, pendulum at rest. Okay, but angular velocity is 0. that is x2 is 0. Okay. Then what happens? Does it remain at rest? It won't remain at rest, that we know physically. So let's see that at pi 0 what is it going to happen. So we saw that f2 is nothing but minus sine x1 minus bx2 minus bx2. Okay. So when you write the partial derivatives of this, you know that dou f2 by dou x1 is nothing but minus cos x1, and dou f2 by dou x2 is minus b. So this is going to be 1 at pi. Okay, and this is going to be minus b. Therefore, the matrix is now going to be 0, 1. For the first equation, anyway, you have 0 and 1 because f1 is nothing but x2. And this one is going to be 1 and minus b. Plus higher order terms. Okay, plus higher order terms. These are higher order terms. So now you look at the eigenvalues. Eigenvalues are going to be lambda equals to minus b by 2 plus minus. It's the same computation, but it's only that you have the 1 in place of minus 1. Therefore, you get plus 1. Okay, so b square plus 4. Now you see that in all the cases you have the b square plus 4, okay, is always going to be greater than b. Okay, it is always going to be greater than b. Therefore, at least one of the eigenvalue that is coming from the plus is going to have a positive real part. One of the eigenvalue is positive. One of the eigenvalue is positive. Therefore, yeah, yes.
B square plus 4 कैसे होगा सर?
I didn't get. Your voice is breaking. Once again.
सर b square plus 4 कैसे होगा? अभी हमने सॉल्व किया था तो सर b square minus 4 आया था और सेम था.
Now the matrix is different, right? Now you write the eigenvalues for this matrix. It is going to be minus lambda, right? 1, 1, and minus b minus lambda, right? So that is a different matrix. That the matrix at pi 0. That is when you evaluate this at 0, then it is going to be minus 1. So here there was an entry of minus 1. Okay, so this is going to be now lambda into b plus lambda minus 1. So this is going to be lambda square plus lambda b minus 1. Okay, so that gives minus b by 2 plus minus half into square root of b square plus 4. Therefore, this point pi 0 is unstable. Okay, so this is going to be an unstable point. Now let's look at the for the same problem. Let us look at the Lyapunov's stability. So we have Lyapunov function. So you have x1 prime equals to x2, and x2 prime is minus sine x1 minus dx2. Okay, so consider there are many ways to define the Lyapunov functions. They are definitely not unique. We take the function v to be equals to b square by 2 into x1 square plus b x1 x2 plus x2 square into x2 square plus 2 into 1 minus cos x1. So you see that this is a function like this. This is a function like this, that is x1, x2, right? This is b square by 2, this is b by 2, b by 2, 1. So this is how it is, the function is written. Okay, so this is basically writing x transpose matrix A to x plus 2 into 1 minus cos x. So you see that this is going to be, you see that 2 into 1 minus cos x1 is always going to be positive, and therefore this is always greater than x transpose Ax. Okay, and we know that this function is going to be, this x transpose Ax is going to be positive because A is a positive definite matrix. You can see that b square by 2 is positive, and b square by 2, how you determine some matrix is positive definite. Okay, so when you look at a matrix like this, this is one of the characterization: A1n, A21, A22, A2n, An1, An. So this matrix A is going to be positive definite if you have this determinants. A11 is positive, and now then look at this determinant and this determinant. So like this, all these determinants are okay. So like positive. If this is the case, then we say that then it is equivalent. That is, A is a positive definite matrix. So here you see that b square by 2 is positive, and the determinant of this is b square by 2 minus b square by 4, which is again positive. Therefore, A is a positive definite matrix. Therefore, this is a positive definite form. What we have taken, this function Vx1, x2 is a positive definite function. From the definitions I gave, I can take the k function belongs to that k of 0 infinity. Okay. Now we look at this function and then write its derivative. Okay. So v of right. So v is e square by 2 x1 square plus p x1 x2 plus x2 square plus 2 minus 2 cos x1. Okay. So write the dv by dt along the paths, that is each x1, x2, or take it as functions of t. So the first one is going to be v square by 2 into 2x1 into x1 prime plus b x1 prime x2 plus b x1 x2 prime plus 2x2 into x2 prime, right, plus 2 sin x1 into x1 prime. Now we substitute the x1 prime and x2 prime, we get b square into x1. x1 prime is nothing but x2, and this is b x2. x1 prime is again going to be x2, okay, plus b x1. x2 prime is what we have, minus sin x1 minus bx2, okay, plus 2x2, again x2 prime, that is minus sin x1 minus bx2, okay, plus 2x2 into sin x1. Now you collect the terms of similar type, and then we cancel the terms of, you see that 2, right? So you have the terms that get cancelled here. 2x2 sin x1 minus 2x2 sin x1, these two get cancelled, they are the same. Okay, and you have the b square x1 x2 and again you have the b square x1 x2. See the b square x1 x2, they get cancelled, they are coming with the opposite signs. Therefore what is left here is bx2 square is bx2 square, yeah, this is this term bx2 square and minus b x1 sin x1, okay, this term, and the next one is minus 2b x2 square. Okay, so this is going to be minus b x2 square minus x1 sin x1. Okay, something like that. So if you see this as x1 goes to 0, right, as x1 goes to 0, for x1 small or x1 less than pi, it is going to be x2 square plus x1 square. Okay, so this is going to be minus b into x1 square plus x2 square for x1 small. Therefore this dv by dt is going to be strictly less than 0 along the trajectories. So this tells us that it is 0 0 is asymptotically stable. Okay, so that is how this Lyapunov theory is applied for studying the stability of the systems. Okay, so I will tell you about some instability theorems. I am not going to prove them. Just give the.
Sir,
Yes.
what can we say about pi 0 from there? Lyapunov theorem. 0 0 is okay, then it is a stable point, but
yeah, so
what
pi 0 you have to again look at different type of functions, right? So it's not going to give this is not going to give at pi 0 you have to see a different one, because you know this is, though dv by dt is less than 0, but there are the trajectory is not going to be completely decreasing trajectory for all values of around x1 equals to pi. Okay, so these are you can see that, but yeah, it's not going to happen. Therefore I'm not doing it here. You have to look for I'll tell you, there is an example which I will tell you that is going to be unstable, right? So how to show the instability in the using Lyapunov, I didn't give the theorems yet. Okay, because we saw from the matrix 1 that pi 0 and minus pi 0 is going to be the unstable critical points. So we don't know how to use Lyapunov's theory still yet for unstability, right? So this is what I'm doing now. Once we do this, then you can check.
Yes, sir. Sir, one more thing. Sir, जो v function construct करता है, इसके बारे में थोड़ा सा और बता दीजिएगा explicitly.
Yeah, so explicitly there is no unique way to construct this, and there is no algorithm to construct the Lyapunov functions. Okay, so if you study sometimes people take, when you have a system, the physical system, they take total energy, but not always the total energy becomes a Lyapunov function. Okay, so even in this case, it is going to be in some sense a total energy. So basically the first Lyapunov function to try here is you integrate this. That is, if you integrate this x2, you get x2 square by 2, and this is the same thing you have, right? So you try the function of the type of integrand, that is minus b into x square by 2, that is what we have, right? And the integral of sin x1, that is going to be 2 into 1 minus x. So this is the first function which people
So your voice is breaking.
Yes, sir, you are not audible.
Okay, let me change my internet to my phone. Yeah. Now you are able to hear me?
Yes, sir.
Okay. So trying the Lyapunov functions is the first ones are take the primitive of this f1 and f2. Okay. So that suggests it's not actually going to become a Lyapunov function. So the first guess is that you can see the when you integrate it, it is going to be minus b into x square and this 2 into 1 minus cos x. So these are the kind of functions, first functions that you will try, and then that is not going to give the asymptotic stability. Then you have to keep trying something like this. Look at some positive definite function plus the 2 into 1 minus cos x, which is coming from the integrand of this. Okay, because you need the function to be a positive definite function, but there is no way that one can guess what the Lyapunov functions can be. Okay. So the whole idea is we are trying to bound the trajectories. So if you see in three-dimensional space, positive definite functions look like this. Okay, so these are the x square plus y square kind of the functions, positive definite function. So you are basically trying to get two positive definite functions kind of a thing where you will bound these trajectories between them. Okay, so the trajectories are going to look like this. So that is the idea. So how these positive definite functions are to be taken is one's own imagination, one's own. Sometimes it comes from the physics of the problem, and sometimes it comes from by taking the primitive of the nonlinearities. Yeah, when you solve more and more problems, then you get an idea of where the terms are getting cancelled and how you get the Lyapunov function and the stability. Of course, if you there is a book which your tutorial teacher will send you. So that has a good account of this stability theorems and their applications in robotics. I'm not an expert of robotics, so that's why I cannot explain you the problems in robotics, but system analysis, normally people call it as engineering. So that book is by an electrical engineer. Okay, so you can see I suggested a chapter 5 of that book. I'm also going to share my notes soon. I'm correcting it now. It's already typed and I'm correcting it now. Once it is done, I will send you maybe in a couple of days. Okay, so what is the okay, so I cannot complete it now, so I have to go somewhere. So I'll stop the lecture today and I will continue the next class. Maybe in your tutorial class, maybe I will convert into a lecture class. I'll see. Okay, I will stop it here. If you have any questions, you can quickly ask me. If you have no questions, okay, so let me take a break.